Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to just kind of go through some examples of finding eigenvectors and eigenvalues for some larger matrices. So up to this point, we've really only done it for 2x2s. And we talked about determinants last time, and if we kind of know how to kind of do some shortcuts with determinants of larger matrices, it kind of makes sense to take some time and just do some eigenvalue, eigenvector problems for larger matrices. So that's kind of the goal for today. To start off, though, I want to show, I want to do this proof. And so we're going to prove that for an n by n matrix A, it's invertible if and only if 0 is not an eigenvalue of A. Right? And conceptually, like really with any proof, I would rather have you guys understand the concept here. And I'm going to use, so let's just do, I'm just going to draw this out. So let's just say we had a matrix that crushes vectors down to this x-axis here, right? So what I'm saying is that the blue, the red, and the green, all after the transformation would appear right here. This is an example, right? These kind of like projection matrices, they're examples of things where you wouldn't be able to invert and go back to knowing where they were. It's unclear if they all are here, were they here, here, and here, or maybe it was even like down here, right? Like we don't know where it came from. So that's what it's saying. And definitely these kind of, these kind of situations, right, are the ones where you have eigenvalues of 0 because you're like crushing, vectors down. I mean, specifically, you would crush like, let's get a different color here. So, if we were taking that yellow vector right there, this vector would get crushed down to literally just the point right there, and that's where you would get like lambda equals 0. So this is like the concept of like what's going on. To prove it, we can do it pretty quick. One thing that I haven't shown too many times, like if you want to prove an if and only if, right, these are the ones where you have to show the forward direction, and then you have to show the backwards direction. And so another way to do it is actually just to make, these are called like equivalencies. Like if you have something that you can basically put this arrow between, then they're equivalent statements. And so you can actually prove an if and only if you can kind of do equivalent statements. You're sort of just doing two things at once. You're going this way and this way. So we can actually do that in this proof really quick. So we know that A invertible is equivalent to the determinant of A not being 0, right? And then if the determinant of A is not 0, that is equivalent to the determinant of A minus 0i not being 0, right? It's just literally throwing in a 0. But, right, this is literally the proof. Determinant of A minus 0i not equal to 0. I think I need to go down here. Is equivalent to 0 is not an eigenvalue. All right? Because that's how we find eigenvalues. We set this thing equals 0 and solve, and we're saying that 0 just can't be an eigenvalue then, right? So this is actually a totally fair way to do the proof. You basically, if you want to do it in two parts, you could think of it this implying that implying that, and then that implying that. That's like the forward direction. And then the backwards direction is start here, just go this implies this, which implies this, which implies that. And so you can do it this way too, to kind of save time. Not all proofs are always like easy to do that way with if and only if. Sometimes the forward and backwards directions are kind of different, but this one works out nice that way. All right. So just kind of to recap, in terms of like terms here. So determinant of a minus lambda I, that is specifically defined as the characteristic polynomial, okay, of a matrix A. If you set it equal to 0 now, that is what we call the characteristic equation of A. And we know that if A is n by n, then the max degree that the characteristic polynomial could be would be n, right? And so with that in mind, the most amount of eigenvectors, or even, I guess, eigenvalues, right, because they kind of go hand in hand, could be n, right? And the theorem in math that basically guarantees all this is really just that fundamental theorem of algebra, which just says that you have n roots for nth degree polynomial. That's basically what it says. There's actually a few different versions of that thing, but more or less that's what it says. And you do have to consider it over the complex plane to get all n roots. And so this is just kind of a good thing to kind of keep in mind. So if we start doing larger matrices, like 3x3s and stuff, we should basically expect to get 3 eigenvectors or eigenvalues. And you might have, like, you know, duplicates. You might get like an eigenvalue of 1 twice or something like that. And then you get like an eigenvalue of 3 or whatever. But and then in that case, you would only get 2 unique eigenvectors out of it. So if you get the duplicate things, and we'll talk all about that, there's going to be some important kind of results related to multiplicity of roots and things. But just know that as we scale up the sizes of these matrices, in a sense, we're also scaling up the quantity of these things that we're finding. All right, so I want to just go through like 2 examples, kind of fully by hand, and then I want to show actually how we can also do this on our calculator. And actually, I think there's going to be 3 examples I'm going to show by hand, but one is kind of quick. So I want to find all the eigenvalues and eigenspaces of this matrix here. So first step, we need to do the determinant of a minus lambda I, all right, and set it equal to 0. That's always where you start. So we're basically going to set 0 equal to the determinant of negative 1 minus lambda, 0, 1, 3 minus lambda, negative 3, 1, 0, negative 1 minus lambda. And, you know, we talked about determinants last time, and we were saying how, you know, probably the most important thing to know is that you don't just need to expand along this top row or this first column or something like that. You can expand along anything, and so you absolutely should expand along this middle column here, right? And you just need to keep in mind the plus minus kind of part of it. So, you know, the pattern is plus, minus, plus, and then minus, plus, minus, plus, minus, plus. And so when we expand along that middle column, we really don't need to consider the zeros at all, right? So we're just going to have a positive expansion along that middle one. I'm going to erase all these things now. Okay, so this determinant will equal negative lambda, because that's really the positive, right? And then times the determinant of negative 1 minus lambda, 1, 1, negative 1 minus lambda. And if you do that determinant out, right, you're going to get negative lambda times negative 1 minus lambda squared, and then minus 1, which if you solve that polynomial, you'll get that lambda like 1, let's say, equals lambda 2 equals 0, and then lambda 3 equals negative 2, okay? And so, you know, going along with what we just got, what we saw in the last slide, this makes sense, right? We're getting really 3 roots for a 3rd degree polynomial, which is what this is, right? And then we just got to go through and do eigenspace stuff. So we don't need to do it like twice or something for this. It doesn't even make sense to do that. We just do one for this, one for this. So when we do a minus 0I augmented with 0, right, you get this matrix out. So actually, I should probably write that this is the RREF of that matrix right there. So what this is saying is that x1 equals x3, and then, x2 and x3 are really just free to be anything. There's no requirements on them, right? So x2 and x3 are free. And so if we do the thing where we just like let, say x2 equal s, x3 equal t, then we basically are getting the span, the eigenspace is the span of s times 0, 1, 0, right? And then plus t times 1, 0, 1. And so, yeah, so we're getting, this plane. This plane is an example of the kind of stuff that doesn't change or stays in its span after the transformation, okay? And then we're going to do RREF of a minus negative 2I augmented with 0. And if we do that one, we get this. All right, and here, so we're getting, that's a 1 there. So x1 equals negative x3, x2 is 3x3, and then in this case, x3 is free. And so you do the same thing, you let like x3 equal like t or something, and you really can use t because like this is a separate thing than this, so you can mix these variables with t, that's fine. And so the eigenspace here is the span of, so we'll do t, and then, let's see, it'll be negative 1, and then 3, and then 1. And so any scalar of that vector will stay in its span after this transformation. And that is, kind of the general feel of a higher order eigenvalue, eigenvector problem. Should feel very similar than a 2x2 one. But I still want to go through a few more examples just to make sure they're really good, because this stuff is like super important for tons of stuff in this course. So I don't actually want to do eigenvectors for this problem. I just want to do eigenvalues. And if you think back to the determinant video, this is one of these. This is a lower triangular matrix, and if you think about it in terms of, you're doing determinant of a minus lambda I to get the eigenvalues, right? You're setting that, I guess, equal to 0, right? If you expand along like, I don't know, just expand along any kind of thing in here, like you could do along here, any of the either first row or last column, you would literally have like 2 minus lambda, times the determinant of 1 minus lambda, then 0, 0, 0, 3 minus lambda, and then 1, 0, 0, 0, and then 7 for negative 2 minus lambda. And then, again, I would go along like, let's say, the top row, right? So you get 2 minus lambda times 1 minus lambda times now the determinant of 3 minus lambda, 0, 4, negative 2 minus lambda. And you can see that you're getting that same nice multiplication on the diagonal, right? And so what this is sort of telling you is that, this determinant right here is really just going to be equal to 2 minus lambda, and then 1 minus lambda, and then 3 minus lambda, and then negative 2 minus lambda. And so that means that the eigenvalues are lambda 1 we can say is 2, lambda 2 can be 1, lambda 3 can be 3, and lambda 4 can be negative 2. But the important takeaway that I want you to see, right? 2, 1, 3, negative 2. I wrote it in a diagonal on purpose. 2, 1, 3, negative 2. If you have one of these triangular matrices, the eigenvalues will always just be the diagonal right there. So I'm just going to write that. That's the important part. Given a upper or lower triangular matrix, the eigenvalues always appear on the diagonal. Exclamation mark. Saves you a bunch of time. And you're going to actually see these, if you keep kind of working with linear algebra, you're going to see a lot of these pop up. Sometimes we even try to construct them because they're so nice. Like there's so many nice properties that occur with them that we would want them, and so we kind of build them up in certain ways. But right now I just want you to see that nice property happening. All right, just want to do one more fully by hand, and then I'm actually gonna talk about how we can use our calculator to help us do some of these problems as well. So probably at this point you're already feeling pretty good with seeing how to find eigenvalues and eigenvectors, but it can't hurt to go through another one because they really are so important. So first step again, determinant of a minus lambda I, set it equal to 0. So in this case, we're going to have minus lambda 1, 0, 0, minus lambda 1, 2, negative 5, 4 minus lambda. And always take some time when you get a determinant, think about where is it going to be easiest to, expand along, like what row or column. The way I'm seeing it, it's either top row or second row. This one's not bad, I guess, too, because there's still a 0. But basically, I'm looking for zeros. And to me, this is a little easier because there's a 1 instead of a 2. So I would just do it along this. So I would get 0 equals negative lambda times negative lambda 1, negative 5, 4 minus lambda, and then minus 1 times the determinant of 0, 1, 2, 4 minus lambda, and then plus 0, but you don't need to worry about that. So this will be 0 equals negative lambda, and then you have negative lambda times 4 minus lambda plus 5 in there. And then you have minus, really 0 minus 2. So you got that. All right. So let's see. Algebra. I'm going to just distribute that in. And then we got a plus 2 really there. So then 0 is, so we're going to have 4 lambda squared minus a lambda cubed minus 5 lambda plus 2, so we have a cubic, which makes sense because it's 3 by 3. So I'm going to switch around all the negatives and make it a positive cubic because we like those better. So I got minus 4 lambda squared plus 5 lambda minus 2. And then this is the thing you got to solve. And, I really believe that a lot of you guys should be able to solve these things by hand. And I know that some of you guys just go to polynomial solvers and do this stuff, but you really should be able to solve these things by hand. This is one where I would do the rational root theorem. And I actually just did it in my Algebra 2 class. If you want to watch that video, I can send it to you. But basically the rational roots of this thing would be of the structure P over Q, and the roots come from, the P would be factors of the negative 2, so 1 or 2, and then the q comes from factors of the first coefficient. And if you don't know what I'm talking about, we really should talk, because you should know this trick, because it's actually really useful. And these can be positive or negative. So you basically have 4 options for roots, right? You have 1, 2, rational roots, 1, 2, -1, -2. And then you can just go and test them. Actually, if you just go test 1, you'll have 1 minus 4, -3, plus 5, 2, and then minus 2 is 0. So it turns out that 1 is a root. So then we could do division. I'm going to just do synthetic division. And again, if you don't know synthetic division, I would also ask, because it's very good to know synthetic division. So we basically have a quadratic now. That's not getting in Algebra 2 mode. So it's lambdas, not x's. Lambda squared minus 3 lambda plus 2 now just needs to equal 0. This thing, even factor's nice. You get lambda, what is it? Minus 2, lambda minus 1. So lambda equals 2 and 1. And so we've got our eigenvalues. We've got 1 showing up twice, multiplicity 2. And then we got 2 showing up just once. Whew, that's just eigen values, okay? But that usually is the most part of it, because the rest of it is honestly like calculator work. So now at this point, you'll just go and do RREF of, let's do the 1 case. So a minus 1i augmented with 0. And in that case, you get this matrix. And then from this one, you can see like x3 can be taken as a free variable. And you would get that the eigen space for 1 would be just like the span of t times 1, 1, 1. And then you do the same thing. We'll do RREF of a minus 2i augmented with 0. And in this case, you get this matrix. And from that one, you can see that the eigenspace for, it's just 2, is the span of 1/4, 1/2, and then 1. And so that is it. We've got these kind of vectors acting as eigenvectors, right? Any scalars on those will stay in their span. And then you've got your eigenvalues right here. And so the last thing I want to show you, I do want to make sure that you can do this process by hand. You can use RREF on your calculators to get that part. I'm fine with that. But eventually you need to know how to do this on your calculator as well. And there are things for that. And that's what I kind of want to just talk about quick here. So if I take the same problem just to kind of show you, I'm only going to go through it. I think most people have the Inspire at this point. But it's possible on like the 89 if you've got that one. It's the same buttons. It's eigvel or eigvec. On the Inspire, you can find it just going menu, and then number 7 is matrix and vector, and then B is advanced, and then 4 and 5 are the eigenvec val buttons. But honestly, you can just type them as well. So you can just type, like, if you wanted to do this on really the 89 or the Inspire. I don't know about 84s. Honestly, I've never done it. I don't know if any of you still use an 84, but I don't think I've ever tried to find eigenvectors or eigenvalues on there. But literally, if you just make a matrix on your calculator and do this, I do think you need parentheses. It's a function that operates on that matrix, right? I'm going to do it right now because you get a weird kind of thing sometimes, and I want to make sure you understand what you're getting. And actually, really quick, I also have this line. You might just want to go to the internet and do these kind of things too. There's like eigenvectors and eigenvalue calculators on the internet, all over the place. It's a super common thing that happens in tons of application problems. So you can also just find it on there. But I want to show you specifically what you would get if you plug this into your calculator. So if I do that right now, this is what I would get. All right, so you should get something kind of like this. I'm getting literally 1 point, and then plus 0.00, a bunch of zeros, then 192, and then an I, like the imaginary number I, and then it goes comma, and then 1 minus 0.00192I, and then comma 2. And there's some stuff I don't quite understand, but I'm 99% sure it has to do with something called floating point error, which is what's going on here. The calculator is, honestly, calculators are just approximation tools. They're not really, they're pretty good with like 2 plus 2. But when it comes with like things like a little more complicated like this, it does some sort of simplification stuff. And like even like programs like Python and things like that, they have these kind of issues too. And so float is like how many kind of decimals you're allowing the calculator to consider in a computation. And because I don't let it just go out to infinity, there's some sort of error with the way the decimals work, is my really weak computer science understanding of how this works. But the way you want to read these things is literally, this just doesn't really contribute anything. This is like, it is 0 times I, basically, and that too. So what it's telling you is the important stuff here is 1, 1, 2 is the eigenvalues. And we got that, right? 1, 1, 2. So those are the eigenvalues. You can just literally ignore that. And you'll get these kind of things a lot. Don't worry about it. For eigenvec, okay, you still just can take it of the matrix. You don't need to take it of you don't need to plug in the minus lambda and stuff like that. And when you do this one, this is what my calculator tells me. Okay, so I think these are all correct. So you should get something that looks like this. So this is, I'm just trying to copy it exactly the way I saw it, and to make it fit, I actually went into settings on my calculator and I adjusted the float, which is going to be the thing that gives you how many decimals. I had it set to 10 and it was like way too much. So I adjusted it to just 3. Actually, this 3 would really not be here. And you also need to let it, sometimes you'll get like non-real result. So make sure you're in like rectangular mode, which allows for some imaginary numbers. But some things to kind of note here. This part is really another thing where it's just doesn't contribute anything because there's an e to the negative 8. So it's like 10 to the negative 8 in there. And same with this one, and same with this one. And I color-coded it because the way the calculator works, if you do it on your calculator, it's going to give you a bunch of rows that with weird decimals, but you want to read it as columns like this. So you'll notice this column is negative 0.577, negative 0.577, negative 0.577. That is the one that basically relates to the first eigenvalue. So the first one here is going to be the first column. The second one here, for second eigenvalue, second column. Third eigenvalue, third column. And, we know that for the 1, we should be getting right here 111, which we get. The reason it's not 111 is because they've normalized it, so they make this length 1. If you find the length of this vector, negative 0.577 all the way down, it's length 1. So that's easier for a lot of computations, which is why they're doing that. This one is truly the same as the 1/4, 1/2, 1. You can see this negative 0.2 is roughly half of that, which is half of that. Again, this is a length 1 vector, which for computational purposes is a lot easier. But you definitely want to make sure you can find them on your calculator too, because we will be using that too.